Hello and welcome to Space Codesign's presentation on our electronics design software called Space Studio, which is meant for rapid hardware software co-design of complex SoC embedded systems. Our software called Space Studio helps you make rapid decisions at the front end of the design process. It operates at the electronic system level, or ESL, at a higher level of abstraction where the modeling reduces the complexity of details so we can handle larger or more complex systems of both hardware and software that must work well together. And one point to please bear in mind during the course of this presentation is that with our technology, you're doing co-design of both hardware and software at the same time. Space Studio is one of the few tools that take you through all three steps of algorithm, architecture, and implementation. Typically, you would start with our module called ELIX, where you would do your functional specification, or some people would like to say algorithm. The main goal in ELIX is to make sure that your behavior is correct. Once you find a correct algorithm, you can then map it, with our help, into SimTech, where you do architectural design exploration. In SimTech, you get more specific about details like processors, buses or channels, what blocks would go into hardware, what blocks would go into software. And if you're running tasks as software on a processor, also the operating system, which has an impact on your performance. The design exploration, particularly when you move function blocks between hardware and software, which is automated in our technology, is reflected by a drag and drop mechanism, which we will show you in a few moments in our demonstration. During your simulation of each architectural candidate, we support you with non-intrusive monitoring as we log transactions that take place in the simulation, and from that log data you can make use of it for performance analysis. Once you have a candidate that you would like to implement, our third module called GenX, which we like to call an implementation manager, can then either map functions to existing IP libraries or put your C, C++ System C code through high-level synthesis, tools such as Synthesizer, Catapult C, AutoESL, or Impulse. Right now, our hardware targets are Xilinx programmable devices, but we feel our API can also accommodate Altera and other vendors. As well, we are seeking a partner for expanding our flow to ASIC. Each of your candidate architectures forms what can be called a virtual platform comprising of parts that come from our library SpaceLib, shown here in the blue, your design IP, shown in the red, either as hardware modules attached to interconnect buses or channels, or as software modules running on processors. They can be simple processors like the Xilinx Microblaze, or more sophisticated processors such as the ARM Cortex-A9. Now a quick demonstration of Space Studio. So here's our Space Studio tool showing the algorithm level or functional specification of a motion JPEG decoder. In ELIX, your modeling is either untimed or loosely timed. All the blocks talk to each other, and the communications channel is generic, either timed functional channel, as we show here in the illustration, or an untimed channel. There are no architectural details like processors or what functions go into hardware or software. The simulation of the algorithm at this level is for verification of behavior. Once you're satisfied with the behavior, you can then move to our architectural design module called SimTech. And so calling up a version of this design that we've targeted towards an ARM technology, we have the motion JPEG components all running on a single CPU. In the upper left, our project window includes a design tree hierarchy. Design tree hierarchy shows you our AXI channel, and to that a number of components attached, including an ARM Cortex-A9 dual core. On the dual core, we have 3 processes or tasks from the motion JPEG attached to the first CPU: demultiplexing, inverse discrete cosine transform, inverse quantization, and zigzag. And on the second one, we have the line builder and the Huffman decoding. We have already run a simulation of this candidate architecture, an all-software configuration. And to look at the logged data from the simulation, we call up our module called Space Monitor. We bring in the binary file that contains the logged information, and then we generate some preliminary graphs. Okay, in the global view, we see that the AXI channel is only loaded to about 11%, so the traffic is not very heavy. There's no communications congestion there. Looking at the 2 processors, we'll look at the first processor, core 0, and we see that it's spending over a quarter of its time idle. Some context switching, some interrupt handling, but when we look at the 3 main tasks for the algorithm, or for the design, we see that they take up maybe 2/3 of the time. That may indicate that they're not processing enough data. And when we look at the other processor, we see that we have 2 large tasks that are taking up the bulk of the cycles on the CPU. Very little context switching, which means that when one is running, the other is idle, and it's not being productive. To me, as an architect, this would seem to be the point of congestion. And I could relieve it in a number of ways. One option might be to introduce more CPUs, more cores, and move one of the functions shown here on core 1, the second CPU, onto the third CPU. One of the arguments against that would be, since I'm using dual core ARMs, is that I may have a 4th processor sitting inactive. So unless I move other tasks onto the 4th processor to make use of the instantiated cores, I may want to consider other options. One possible option would be taking the Huffman decoding or the line builder and moving it from software running on a processor to hardware as a coprocessor sitting on the channel. So let's do that. Now previously, if you had C++ code written for a CPU and you wanted to implement the function as hardware, you would have to run out and find a model for, let's say, Huffman decoding written in either VHDL or Verilog. But here we're operating in System C, and we're considering everything as a function, only to be retargeted towards either hardware or software. So let's take the Huffman decoder here, which is now software, and let's transform it into hardware. There's no recoding. Instead, as we move this onto our bus, voila, our Huffman decoder is now shown here in the graphic as a hardware block. In the design tree hierarchy, we still see that we have the same 3 tasks assigned to the first processor, whereas line builder now occupies the second CPU solo. So now that I have a new topology, what I need to do is clean out some of the old files that were generated from the previous configuration, and then regenerate the top-level file for this new candidate architecture with monitoring in order to look at our simulation results, as well as generating other support files such as linker scripts, since our software load setup is now different, make files, and also communications analysis to look at optimizing communications between hardware blocks. And so we now finished generating our new files, and then we have to compile them. And then in the compilation or build step, first thing that happens is that the hardware is compiled by the OSCE System C compiler, which is a GNU compiler, open source. And then our software tasks that run on the processor are then compiled using, in this case, a GNU compiler, a version created by Code Sorcery. So now we have the software compiling, and that's finished. Voila. So now next step is to run the simulation of our new candidate architecture. And in this motion JPEG example, what happens is that we take a motion JPEG stream and extract 2 frames from it and then paint it on the simulated VGA display. And and right now what you see in the simulation output is the setup for the binary files that log the transactions, and you should see now the first line being painted for the motion JPEG example of 2 JPEG frames. So while it's painting the 2 JPEG frames, I'd like to resume the presentation, since otherwise this does take 3 minutes. And if we resume our presentation, we talked about how each candidate architecture that we create during the design exploration forms a virtual platform. You've just seen 2 in the Simtech architecture level editor. The first one was all software, where all of your red blocks, your unique IP designs, were placed on CPUs. And then using the drag and drop mechanism that reflects the automation of the hardware-software partitioning, we dragged and dropped one of the blocks, the Huffman coder, from a processor onto a bus to be implemented as hardware in the new virtual platform that we're now simulating. Mention that in the example we used the ARM Cortex-A9 dual core, which is one of the most popular processors in mobile at the moment, as well as the processors selected by both Xilinx and Altera for the new flagship programmable devices. We also offer support for the Leon 3, which is popular in the aerospace sector, as well as the Xilinx Microblaze, which is the classic CPU used by Xilinx. In devising each candidate architecture, you're looking at goals of either performance, power, or hardware resource consumption. Traditionally, the process takes place on separate hardware and software tracks, and then later on, the hardware and software is then integrated and likely modified in order to make them work together. But the one takeaway I'd like you to have from this slide is the X that we see here, which symbolizes how the hardware and the software in a co-design scenario is being created together, and one knows about the other. We've shown you pie charts generated for the CPU cycles consumed by all of the tasks during a simulation run. Some of the other charts that you can devise from the transaction data that you log include Gantt charts to show you things like task scheduling on a CPU or traffic on a bus or channel, as well as the pie chart that we shown you earlier in analyzing the first all-software architecture design. Some of the other types of information that you can build from the logged data include things like memory usage, where you can look at memory heat maps, looking at the interconnect bandwidth usage, processor load, which we had just shown you with the pie charts, and task scheduling and context switching, as expressed by the Gantt chart from the previous slide. And then when you have a candidate architecture to implement, you can then run co-synthesis through Space Studio. In this example, what we show is on the left one of our windows where you set up the target and the board support package that goes along with the device, in this case the Xilinx Zinc, the new flagship platform from Xilinx. On the right side shows you output from Xilinx's own resource estimator, and some of the top-level information we back annotate into Space Studio. Again, on the left, where in the lower section you see graphs indicating the resource usage on your target device. What that tells you, most importantly, is whether or not your design fits on a particular device. And if it does, maybe, just maybe, you have enough space left over that you could examine going to the next smaller device in order to save on things like cost, footprint, and power consumption. One of the things about our Space Studio tool is that it does fulfill 3 areas in ESL of virtual prototyping that was identified by Gary Smith, a leading industry analyst. Space Studio also offers a 4th advantage, the automated hardware-software partitioning that you saw reflected by the drag-and-drop mechanism, where you don't have to translate your C, C++ System C model between hardware or software. You use the same model. Our Space Studio platform is scalable. We in the future will be adding new CPUs, new operating systems, and new interconnect networks. And we have access to an innovation pipeline from the École Polytechnique in Montreal, where the original research behind Space Studio was performed. Some of the target markets that can make use of Space Studio include markets in aerospace and avionics, automotive, as well as multimedia and wireless, and other commercial areas such as high-performance computing. So let's go back to our demonstration and see, okay, we now have the second frame generated. So let's stop the simulation of the new candidate, and just as a refresher, our second candidate was not all software like the first, but had one function, the Huffman decoder, moved into hardware. So let's see how this candidate performed. Here we intake the binary files that logged all the transactions, and we generate the top-level graphs, and even top-level graphs tell us a lot. Bandwidth utilization went up by 1% from 11 to 12. That makes sense, since data is being communicated between the Huffman decoding block and the tasks in the processor. Now we look at the CPUs, and both of them are busy. Now, this could be a good busy or a bad busy. Okay, the first CPU that had the IDCT, inverse quantization, and the multiplexing, we see that the idle is now cut down to 1/3 of what it once was, just under 8%. Before it was over 25%. This tells me that the 3 main tasks, inverse quantization, inverse DCT, and demultiplexing, all have more data to process, so they took up more CPU cycles. The first processor was definitely more productive. Look at the second processor. Line Builder has the second processor all to itself, and it's making good use of it, taking up nearly 94% of the time. It's only idle maybe 6% of the time, with little interprocessing and almost no context switching. In fact, the context switching may have been just the operating system regularly just waking up to check and see if there was any task to preempt, but if there wasn't, then no need to. What this tells me is that the Line Builder was working at its maximum possible for this particular design candidate. It may not be the fastest candidate architecture that we can come up with, but it is definitely faster, higher performance than the previous one. And with that, our demonstration concludes. Again, if you were using Space Studio to examine your motion JPEG design, you would be examining other candidates as well. So if this interests you, please make use of this contact data to either call our distributors in the United States or in East Asia, EDATEC for Servant Technology. If you're located in Europe, please contact our European Operations Director, Jean-Jacques, who's located in Paris, or please visit us online. And with that, thank you very much.